Thank you. So can everyone hear me clearly? That's good. Okay, good. So yeah, so first I would like to thank the organizers and especially Yang Hui for inviting me to this nice symposium honoring mathematician S.S. Chen. And so Yang Hui was telling me that this is going to be a kind of mixture of kind of physicists and mathematician and other scientists in the audience. And so he asked me to talk about something which of a kind of wider interest and engaging. So yeah, so I decided to talk about some of this, my recent dabble, like done in collaboration in the past year or so with Yang Hui and a couple of collaborators who might be speaking in this symposium. Basically machine learning of physical symmetries, well, symmetry in our physical system. And I guess in hindsight, this might be quite appropriate in this occasion, really, because I guess S.S. Chen was known as a great teacher in his days, and of course, his influences is not just in the pure mathematics, but many of the maths he discovered that also apply to physicists. So yeah, so basically today's talk is kind of my dabbling into trying to see if we could actually also teach machines something about mathematics, and also hopefully, well, it's kind of physicist oriented, and it might help us to tackle some physical problems like in the long run. Okay, so let's start it. So, oops, let me see if I could get this slides moving, and already have a machine mode functioning to begin with. So let me see if I could let me, oops. How do I go to the next one on this? Oops.
I don't know.
Okay, let me quit this, leave this. No, I don't want to leave the meeting. I want to stop sharing and I want to, oops, no, I don't want to have a VPN. And if I share again, let's see if this works better. Okay, very good.
Left and right. Very good.
That helps.
Thank you.
Okay,
thanks.
Good. So yeah, so machine learning, I guess among many kind of ubiquitous application nowadays, starting from AlphaGos and other, for example, application in finances, probably one of the kind of most frequently encountered machine learning application nowadays is actually like facial recognition, right? When you actually try to look at your iPhone and try to unlock it, or nowadays even apply to, like, for example, banking applications on your phone, that require actually recognizing your facial features. So typically, so here is a kind of a picture of human faces. You try to, as a kind of first sketch from a machine perspective, that we locate some vertices on your faces, and the machine start trying to kind of truncate your faces. And of course, our faces are three-dimensional objects, so eventually this is something similar to triangulations. So slightly more detail, yeah, I guess right now the kind of state-of-the-art kind of facial recognition, well, probably coming from the Facebook, suited enough that you collect all the faces from the photo you uploaded, and among invading all your various privacies and so on, is using your faces to train its machine. So this is a kind of illustration about the kind of neural network infrastructure that Facebook is using, and this is Callista Flockhart, and who was probably last famous in the previous century due to Ally McBeal. And so they use her faces as the illustration from this 2004 deep face paper. I guess now the technology probably improved a little bit more. But roughly speaking, that as a first layer from this neural network that we basically apply like we do with castle ray television, that we have the red, blue, and green, three different colors, and we kind of just partition our faces into a number of pixels, and then we try to use a multi-layer of filters in the next stage, and we're trying to use those filter to capture different kind of facial features and so on. So I guess at the time in 2014, and I'm happy if somebody in the audience can update me on this, that in those days we could already capture like 4,000 different facial features, and basically we can recognize at the time that machine can already recognize that human faces up to 97.35 accuracy. And I guess slightly beating according to their table in this deep face paper at the time. That is still, I think human is about 90.5. Basically, we're trying to recognize somebody who's never seen before in the wild, and from the data we're trying to spot this person in terms of this kind of accuracy. And human, I think, is slightly higher. I wonder if nowadays that this is actually improved even further. But anyway, so that was one of the classic machine learning application. And of course, another one for machine learning application is actually faking those faces. After Facebook collecting all these features from us, and then we're starting to use those features that, all these faces you must have played and been fooled by this kind of game already, that none of them actually exist. And this is coming from, this website. This person does not exist.com. But nice thing about it is that we can actually instruct the machine based on what you wanted, right? All these different features we tabulated earlier, such as the hair color, your skin color, ethnicity, genders, emotions, even like, for example, symmetries of your faces, that whether your nose is slightly tilted at one side or the other, and so on. And then machine basically cook out something, resemble human faces and enough to fool you, right? So that's another very useful, well, I don't know if it's useful application of machine learning. But okay, so enough of kind of general rambling. So, but this task, these two tasks are kind of similar. Well, okay, in a kind of very stretch of the imagination sense, that it's kind of what physicists, or as a subset of scientists, really do. Right. So often, of course, in the more abstract senses, that we will encode things in equation and mathematics and so on. But roughly speaking, what we normally do is that we collect and kind of record experimental, or sometimes coming from numerical study like the lattice QCD, like certain observable, and we take the measurements, like could be a length or tense, or for example time and all that, and then we like to classify them. I would like to classify them based on some underlying principles. And sometime after some amount of eyeballing, then we realize, aha, this class of this observable actually has some underlying guiding principle, what physicists usually know as the symmetries. And of course, physicists have plenty of those things. We can be looking at the global symmetry. It could be a discrete one, and it could be a continuous one. And of course, there are local symmetry. And of course, there's a treasure kind of space-time symmetry. We're looking at the Lorentz symmetry or conformal symmetry. And then, once we figure out those kind of symmetries, then we usually use them as some kind of guiding principles, sometimes to construct the kind of viable physical observables that we want to calculate, or actually test it against experiment, or sometimes even better, right? The symmetry is so constraining that usually appear in the context of theory or even in supergravity, that the symmetry alone is enough to allow us to actually come out with the entire series. All right, so these two things, I guess the first part is kind of similar to collecting the human faces. And the second part here is that after we know the features of those human faces, then we use them to actually cook out something that has a new faces or new series, which are actually at least viable against all the current physical understanding. So so at least in my opinion, at least that's how I get into this kind of game, thanks to Yang Hui actually. So it's kind of desirable, or at least exploratory, to ask if a machine is actually capable of learning about certain aspects of some of the important symmetry that appear in our physical system of interest. And I guess I would take a slightly more agonistic view about this. I wouldn't want to go grandiose saying that machine learning, at least from my perspective and from my knowledge at this moment, that actually allow us to kind of coming out with new physical theory or in the immediate danger of a replace a theoretical physicist. But I think the following tests I'm going to talk about are more like collecting the useful machine learning pieces which hopefully one day that we can actually fit those different pieces together and actually help us tackle real interesting physics problem which we otherwise cannot do. Okay, so that's kind of my philosophy slides up to this stage. So any questions so far before I proceed? Okay, very good. Okay, so probably the most widely used language for physicists to classify symmetry is basically the Lie group. So the first part of this talk, then we want to ask, well, are there some aspects of Lie group or Lie algebra are actually machine learnable? And I think this is actually a key word in this game, at least for my kind of limited experience playing with it for the time being. That is how to actually phrase something which is interesting to physicists and perhaps mathematicians, that in a way that machine can actually help you do something. So this is one example. So for example, if we consider a irreducible representation, let's call it RV, and the V here is the wave vector. And so let's just look at the SUn+1 for simplicity. And so all these are kind of the highest weight. And so what do we normally do as physicists? Well, so we take two of them, we consider the tensor product, and this kind of things, it happens, for example, like two particles scatter off each other, and you ask, okay, at the other side of the scattering process, right, assuming the symmetry is not broken, then we want to label the outcome as a kind of a direct sum of all this tensor decomposition. So here, the W here label all the possible irreducible representation, and the A here is some positive integer to label the possible, basically the multiplicity associated with each of the irreducible representation. So here we define a quantity. I guess it's not too hard. It's actually length of the distinct irreducible representation out of a tensor product. So for example, if we consider the SU4, and if we take those two representations, so it contains the two, this would be SU3. So let's take this one. Okay, for the sake of argument, let's take this one for SU4, and here there are 5 distinct irreducible representation in our product. So I will call these things as a length 5. And then the first one is actually for SU3, then it actually has a length 3. Okay, no big deal. This you can get your good student to work on it. But I guess the problem here is really a priori. Without actually doing the tensor product, you actually don't know what's the length of this decomposition, or basically how many terms, how many different kind of distinct particles you can actually get out of smashing two of the given particle together. And this actually get pretty bad, actually. I mean, the simple example just now was probably not highlighting enough. So we use this Mathematica package, this thing called LiArt, and use it. It's very good. So we consider kind of randomize the rank of the SUn+1 gauge group, and we also kind of randomize the weight vector, so you can take arbitrary values in those two weight vector involving taking the tensor products. And of course, we have limited computational power, so we try to truncate the total dimension of individual irreducible representation, which coming out from the tensor product at about 10,000 But this is what we found. So this table here is indicating that so the the horizontal axis here is actually indicating the length of the tensor product, basically how many terms when you smash those together were generated. And the vertical axis is how many times each of those given lengths will actually appear out of this. So we generate about 10,000 data from here, 10,000 data from this kind of randomized process as well. So it's a pretty kind of wild distribution. Naively, yeah, you do expect, when the number of the product gets, basically the length gets longer and longer when you have more and more products, then it kind of decays. General trend looks, this like that. But you still see this kind of funny little bump. At least that's what we saw here. If some mathematician in the audience knows how to do this general counting, we would really appreciate. Then we have a curve to actually kind of match against. But okay, so that's kind of the data we are using trying to train the machine. So what do we ask it to do? Well, so we basically want to consider a binary classification task. And the question here is that whether the machine can actually distinguish a tensor decomposition with a length above or below a certain given value. So for example, let's say, we just have all this Lie group and tensor product. Let's say, can machine tell you that whether this tensor product it contains more than, say, 70 different terms, or less greater than that? So that's the question we want to ask the machine. And for those of you who know a little bit of machine learning or been playing with it a little bit, this is the kind of neural network architecture we use in our paper for doing this training. So here we choose this cutoff, right, for below and above to be 70, and the reason we choose this for the AM or SUN case, n+1 case, is really that we have 10,000 data point, and this roughly cut in the middle that divide into 5,000 each. And this, of course, is an artificial choice. In fact, that we try this out with, for example, other different cutoff, then you have a data like 20/80 splitting or other ratio you want. But this is what we saw. So basically, that of course we also do the splitting of the test and the training data. And so for the case of 5,000 and with this data training data, machine was actually able to reach the accuracy of it's basically the same kind of cat and dog training you might have seen in some popular article. Now it's just our cat and dog now become below certain cutoff. Actually, after maybe it's better to show it didn't quite label. It does. The number of epochs that basically you can also view this as amount of time. Then this is probably like of order 10 order of minutes actually to run this number of epoch based on our infrastructure, that we quickly reach a very high accuracy of kind of 97%. And to make sure that we actually not, for example, the machine is not doing any kind of false positive or false negative, then we also use this very common measure of a so-called Matthews phi coefficient to compute the confidence of our training result. And this actually gives us also around 93%. And we also tested with other simple Lie group. Now we can actually have use a different kind of a cutoff length. And again, we see that machine reach a pretty high accuracy. And I think the cases for G2 and the E6, that was largely down to actually taking very much time, a lot of time to actually generate enough of a training data to begin with. So the resultant accuracy is comparably lower than those simpler cases. Okay, so And this is the well, for the people who are playing with machine learning right now, these are our kind of loss function, and this is our error rate. So we can see that things very quickly kind of converges after, let's say, around 25 epochs for our network. And here the orange color is our training curve, and this blue one is our validation. So they kind of converge pretty nicely there. So we actually try to take care of this possible overfitting issue as well. So yeah, so when we kind of do the data with a different kind of split, like by varying value of L, again, we see the accuracy and confidence level remain very, very high. So yeah, so from this kind of very simple test, yeah, this is one of the features that, for example, we ask machine to test, and the machine, is pretty much up to the task. So in fact, we can try to do a little bit better in this game. That we can also ask, okay, just now we were just, feeding machine all the data that with the irreducible representation less than 10,000 dimensions. But you may not want to do all this, right? Because it's going to take longer to train. So we can also try to ask the user data that with only dimensional irreducible representation, like less than 2,000, let's say. And using alone, train the machine to perform the binary classification task for those larger guys. And this is what we found. Again, this is actually very, kind of promising. The machine, again, it's kind of extrapolation. Yeah, if you want, we're using a lower dimensional data to actually train the machine and ask it to extrapolate the higher dimensional guys. And again, we see a very good accuracy and confidence level in the training results. So so for this kind of problem, so I would say in this talk, most of them I'm trying to illustrate that those are the problems machines are good at, and whether this is useful to physicists, I will open that to interpretation for the time being. So that's the attitude I'm taking. Okay. So I'm shooting myself, but I think we need to be honest. So, okay. So another question might be of interest to physicists is that we can also ask, can machine learn about the branching law of a Lie algebra? So more specifically, that given a certain irreducible representation of a Lie group, all right, and it contains a maximal subgroup, then can machine actually predict if this irreducible representation actually contains some of the irreducible representation of its maximal subgroup? And of course, this is somewhat physics, motivated. Like, for example, if you want to use the SU5 guts, and you have some fields in the SU5 guts, and you want to ask whether we can kind of decompose this into the standard model context. So it turns out this is actually difficult question to answer, at least time consuming. That's the best way to say it. So of course, for your garden variety representation, the small one, you just do it. But let's say if you have a sufficiently large representation, let's take, I don't know why you would consider 10, 10, 10, 10 of SU5. But let's say if you want to do it. And so this is a plot, right? This is the time taken. So the horizontal axis here is the length of the weight vector. Actually, more precisely, we consider all the weight vector have an equal entries here. So this 1, 2, 3, 4, 5, 7 simply means it's 1, 1, 1, then 2, 2, 2, 3, 3, 3 here. And then the time taken for this Lie art to do the decomposition into 3 times SU, 2 times U1 in seconds. And this is a log plot. I guess there's a warning that it's a log plot. So by extrapolation, and for 10, 10, 10, 10, roughly we need 20 years to do this decomposition. Then you can answer, okay, whether you're starting with this guy, whether your, I don't know, standard model quark actually live in this thing precisely. So yeah, that's the kind of problem we are facing here. So in terms of machine learning help a little bit, well, quite a bit here actually. Yeah, I would say at least for SU5 case. So we consider the question that finding a bifundamental, so fix this subgroup, the representation of the subgroup, to be bifundamental in SU3 times SU2, and then we allow for arbitrary integer U1 charges. So using the 800 smallest irreducible representation as a training data, actually this is a pretty small number if you think about it. And then we do this kind of splitting of a training, validation, and test data split. We reach about, almost 90%. And the confidence level is about 80%. And that was using the neural network architecture presented earlier. And if you use a slightly different, this thing called support vector machine, then this will actually have slightly lower accuracy and confidence. So in other words, okay, I don't know if this is a good way to phrase it. So suppose today you want to, your phenomenologist friend, okay, maybe they won't ask this question, but then they will just say, okay, can you tell me what's the chance of me finding a bifundamental from SU5 and transforming standard model? Yeah, to 90%, I can tell you it's there. But for other group, G2, for example, this is a bit tricky. And we still haven't got quite a clue whether it's just due to the lack of training data or what. But so the question we ask is similar, that we consider SU2 times SU2 maximum group of G2. And in this case, G2 is large, but the representation is large. So we have to truncate this at 4.7 million, do the same game. And in this case, that actually the machine is no better than like 50-50, yes or no, basically. It's like, yes, it contains, it doesn't. No better than this kind of blind flip a coin answer. So I would say for this kind of test, the judge is still out there. Maybe we should, other different group. Of course, I mean, here we have some physicists in mind. Of course, SU5 and G2 are popular among physicists doing the kind of model building. But maybe for some other simple Lie group, we can also try to play similar kind of game and see what comes out. So that's another thing. Okay. So let me switch gear with, so that just now, I guess those are kind of internal symmetry. So let me also try to ask whether a machine can also learn something about space-time symmetry. And in this case, the conformal symmetry. And the keyword here again is trying to phrase your question into the binary classification. So so the question we ask is that, okay, if the machine can actually distinguish between scale and the conformal invariance, and here our training data are the correlation functions for the conformal primary operators. So just a couple of words about the primary operator, that they are usually labeled by, those are local operator labeled by scaling dimension denoted by delta, basically telling you that when you scale your space-time coordinate x by lambda, then this operator will scale as a lambda to the minus delta. So the difference between the conformal invariance and also the scale invariance is that if you only have a conformal invariance, then this only allows you to fix the 2-point correlation function for the two primary operator to be the following form. But now if you also add the spatial conformal transformation, or you can view that the kind of scale invariant symmetry as a subgroup of the full conformal symmetry, then there's an additional requirement that the delta I and delta j has to be equal to each other. Otherwise, this thing vanishes. And for 3-point, this is even more constraining, that if you only have the scale invariance, that only allow you to fix your 3-point correlation function to be the following form, and A, B, C are just some random partition of your 3 different scaling dimensions. But now if you supply this with a conformal symmetry, then this is unique. That is a unique combination of the three scaling dimension involved. So those are going to be our training data. So we basically ask the question that, so let me be more precise. So yes, so we're going to ask the machine to distinguish two different type of function, that the scale invariant correlation invariant three-point correlation function. And here, admittedly, that we don't have any physical theory in mind. So the delta I here are just randomly generated values. So we are not imposing any of the crossing symmetry or the fancy bootstrap. That's next level up. We are not claiming we are doing this. But right now, we just simply ask the question that can machine, now if we randomly select those insertion point and also the scaling dimension, can they classify? Can machine tell the differences? And the answer is yes. For this kind of problem, again, machine quickly, here we actually, even with a fewer training cycles that are less than 20, that will quickly reach the, using the 10,000 training data point and 5,000 of each kind, that we can reach the 95% accuracy very, very quickly. So it's kind of good for that. And another thing we ask, this might be slightly more interesting, is, since we are playing with conformal field theory, the operator product expansion is actually a very important tool for us in conformal field theory. And of course, Bootstrap is all about this. So here we play the simplest example, one dimension CFT. So here there's also a conformal, OP expansion in terms of conformal block. So we're looking now at 4-point correlation function, and we make it simple that everything is scalar. Well, one dimension is really only scalar. So and there's only one cross ratio since we are in the one dimension. So the C here is the square of the OP coefficient for the particular exchange operator labeled by scaling dimension H. And the remaining function here is the one-dimensional conformal block. So you can really view this. I mean, for the novice, I mean, for mathematician or student, you can just, this is a fancy version of the Fourier expansion, but instead of having the circular periodic symmetry, you have the conformal symmetry. All right, so we want to ask the question that by looking at the left-hand side, basically the correlation function, can machine actually be trained to tell the differences between the right-hand side contain a particular exchange operator or expansion mode or not, basically presence or absence of a particular term? So few technical warning here. Of course, in general, expansion here, this will be an infinite sum. Okay, most of the OP expansion, unless there are things that Ising model, there are some truncations and so on. This is an infinite sum. That will create computational power, of course. So we have to do a kind of artificial truncation, and also that usually scaling dimension are continuous value as well. So this would now we actually, as a kind of a toy example, we make them integer. So we can actually do even simpler thing. In fact, let's just do Fourier mode expansion. In this case, then we restrict ourselves x between pi and minus pi, and we only look at the sign as a basis. So yeah, it's the same question. Now we ask, can machine distinguish f of x with or without certain n, right, certain sign nx? So we truncate this infinite expansion and only to 4, just being lazy, but we're trying to illustrate the principle here. Now, let's say if the n equal to 2, this mode is missing. So you have 2 different class of function. So we kind of, again, bit by bit, we're reducing this whole problem into a binary classification. And once we can do that, the machine is perfect for this task. That it can very quickly well, we can very quickly generate data to begin with. And then you can quickly distinguish with high accuracy that the n equals 2 modes with or without the two different kind of function. We can classify it very, very quickly to high accuracy. Okay, so this is probably my last slide. So for the case of the conformal expansion, so we really feed in those hypergeometry function, and we do slightly better here. That, of course, this is a very unphysical assumption that we make the scaling dimension to be integer in this case, and we keep it to 10 terms, and machine again that can very quickly classify the differences of two different correlation functions. You can interpret it as saying, okay, let's suppose if you have you want to ask a question, is this sensitive to the presence? Well, you can revert the logic. I guess you can reverse the logic that where the machine, by looking at the correlation function, which is something really observed in the CFT, right? You don't really see individual conformal block. Right-hand side, left-hand side is what you really see. Then based on the form of those correlation function, machine will be able to tell you with a good accuracy that this guy contains this particular exchange operator. This guy doesn't. So that's the problem we're asking. And machine was quite efficient in telling you the answer for this. Okay, so in this talk, I basically present the based on trying to reduce the problem into binary classification that one machine can learn about. A few examples that learn about the symmetries that appear in the physical system. So like I said, I would say that those things are really just small building pieces which eventually we want to put them together in tackling and formulating the interesting physics problem that we can use those things machines are good at to actually solve. So the obvious things missing here. One is the kind of realistic training data. So for example, if you let's say if you want to ask machine to really do the conformal bootstrap for you, probably what would be needing here is that the realistic, a full understanding of all the spectrum, CFT data, and OPE coefficient of enough number of CFTs. But that's very hard. If we know that, we probably don't need to have all this recent breakthrough of bootstrap already. But maybe in the case of 2-dimension, we can make a progress on that. There are a lot of data for this. And of course, all these things that I just now was trying to emphasize, that the scaling dimension, all that, there was no crossing symmetry imposed on them. So this kind of physical principle need to be instilled in machine to really learn about the physics side, I would say. And eventually that, we move towards that maybe machine will actually figure out what's the kind of underlying physical theory. And my dream was really that by doing this part, the machine can actually tell you when we're feeding, for example, given a CFT, feeding some low-lying, after training enough, feeding some low-lying CFT data like scaling dimension and coefficient, and it just immediately predicts the rest of the story. But that might be too crazy to think, or at least we have to be very optimistic about this. So I guess people can return to watch Olympic now. Okay, so I'll end my talk here.
Okay. Thank you, Heng-Yu. Thanks. Are there questions for Heng-Yu, either through the chat or directly? Please just unmute yourself. Yeah.
I have one question, if I may.
Please,
Daniel. Okay, hi. Yeah, please.
Hi. Thanks very much for the very nice talk. So for the first application for the irreducible representations, I think your input was 2 vectors, right? And if you switch them around, you should get the same output, right?
You mean, okay, yes. You mean like, for example, if we recover the tensor product? That's what you're asking.
No, I mean, so like this machine learning problem has some symmetry. Like if you switch the two vectors of which you take the tensor product, the output stays the same, right? And so the other problems, there I didn't really understand what exactly was your input, and like, does this have some symmetry, the other problems that you explained?
Let me try to understand. So you are saying if I switch those two guys, and then what do you want? You mean the second?
So I mean, you're here on this slide where you write down your neural network on the previous slide.
This one, okay.
Yeah. So there, your input is a 2 × 8 matrix, and your output is a number. And I'm saying if you switch the 2 rows of the matrix, the output should be the same.
Right.
Yeah.
Yeah, I think we tested that. Yeah. Okay.
Yeah, and now, so the question is, for the other problems that you explained in the end, is there some symmetry like this going on?
You mean this one, the decomposition, or this one, the low representation, or?
No, I mean the 2 last problems. The
one about the conformal field theory one. Okay.
Yes.
This one. Let's see. How do I understand that? No. But to begin with, this case, I'm not taking the. So what would be the analog of doing this? You might saying, for example, this would be like a permuting the scaling dimensions. Is that right? Or I'm even trying to understand what, in this context, what you mean by
if I understand
permuting the 2 tensor product.
If I understand Daniel's question, yeah, it would seem to look at some kind of discrete symmetry by exchanging the conformal dimensions of the operators in the left-hand side.
Right. Yeah, that's what I was saying. That maybe it's permuting the scaling dimension. I'm not sure if we tested on this yet. Actually, yeah, I don't think we tested on this on our code because we just didn't. Well, no, actually, we have. I mean, yeah, okay, fine, sure. Permuting the scaling dimension just means okay, you are saying permuting those guys, but not the insertion point. Probably that's the point, right? Most precisely. Yeah, I don't think we have done this, but I believe this one, yes, this is yeah, actually, I think based on the data we generated, we probably include all these permuting cases as well. Yeah, but I probably need to check. I don't want to make a.
Maybe you can make a comment.
Yeah, maybe Yang Hui can say something. Yeah.
No, I just want to make a comment because I know Daniel very well, and Daniel likes to build symmetries into the neural network to make the structure of the neural network aware of the symmetries of the problem. That's a good point. I think what we did here was just to try to generate a full, a dense layer that would just do the transformation. I think it will be interesting to try to see that. But since with just with a full linear layer, we're already getting such good results. We're happy anyway.
Right.
But yeah, I think what Daniel is getting at is whether we could devise have interpretable in the layers, as to why the symmetries have been picked up, which is certainly a thing to try.
I see.
Yeah, that's a good point.
Yeah.
Okay, thanks.
Yeah, that all makes sense. Thanks for the answer or answers.
Yeah.
Okay, great. Other comments, or there's somebody in the chat?
Yeah, there is something in the chat.
Could machine learn to distinguish more than 2 kinds of symmetry? This will be beyond binary classification. Yeah, that's a. Let's see. So actually, in our paper, okay, let's see. Okay, I can say what we did in the paper. Yeah, we still have to break into pieces of. Well, we did consider, there are ZN symmetry that we touch it. ZN global symmetry in addition to the conformal symmetries. We did look at the 3D Ising model, some of the data there in our paper. But yeah, I think at least what we did, we still need to break into pieces. First, looking at the Z3 discrete symmetry as formulated as a binary problem, and then we restrict it to then we consider the CFT as well. So basically, among all the Z3 invariant, let's say 3-point function or so, and then we consider the scale or conformal symmetry, like what we did here. Yeah, but I think that's good enough. In my mind, that seems to be, if you can break all these individual symmetries, that step by step and put the code together, I don't see it's any worse. I guess. I mean, yeah, that's why I can comment.
Okay, so in the interest of keeping minimally the schedule, let's thank Heng-Yu again for a very interesting talk.
Okay, thank you very much for your attention. Yeah, thanks for the opportunity.